I'd like to thank you all for taking the time to be here. This is my senior project. I'm super excited to share with all of you my really weird and irrational interest with astrophysics, specifically around black holes. And during this presentation, I came up with, at least as far as I could tell, an original idea around black holes. I'm not gonna spoil too much, so let's just get ready to it. Alrighty. So, just big question about this presentation that at least I came up with was, how did black holes, probably what you could think of the most destructive objects in the universe, pave the road to life? I think it's a good place to probably just start from the very, very beginning, talk about what life requires just in general. Okay, so if any of you have taken biology, I'm sure you've seen this little, the acronym here, CHNOPS. We have carbon, hydrogen, oxygen, phosphorus, sulfur. Why do these matter? Well, we have carbon, I call it the life element. Without carbon, there is no life. Hydrogen, key component in almost all life. It's a key component in water, most organic molecules, and it makes up about 75% of matter in the entire universe. We have nitrogen, it's crucial for amino acids, nucleotides, which build proteins, DNA, RNA, etc. Oxygen, well, much like hydrogen, it's very common in water and other organic molecules. Phosphorus, without phosphorus, DNA is impossible. I'm sure you've all seen the nucleotides, most of them are phosphorus bases. Sulfur, without sulfur, there's no proteins. And without proteins, there is no life, period. Okay. Right after the Big Bang, this was most of the universe. About 75% hydrogen, as it's kind of stayed the same most of the time, about 25% helium, and less than 0.01% lithium. It was a primeval soup. It was unbelievably hot at billions of degrees Celsius, it was really hot, all this stuff together. But where did these other elements come from? I mean, the periodic table is massive. If it was just made of mostly these three elements, where are the other coming from? Well, concept probably most of you have seen, nuclear fusion. Under extreme heat and pressure, atomic nuclei get forced together through this process called nuclear fusion. They overcome their natural repulsion to each other and smash into each other, creating a new element. This is a common one. You have deuterium and tritium. These are hydrogen isotopes smashing into each other to create helium with a neutron flinging off, and that neutron can go and cause other fusion reactions elsewhere. But for this to happen, like I said, it needs to be under extreme conditions, pressure and heat. And if the universe, well, as you know, it expanded really fast. So how is it dense enough for all of this to happen? Well, a force had to bring it together, right? And that's a force I'm sure you're all very familiar with. It's, well, gravity. It's the force that set up life. Newton, as I'm sure you heard of, thought of gravity as a traditional force. He defined it using this equation. He's got the gravitational constant times mass 1, mass 2 over r. This was not totally inaccurate. It works, but it wasn't the whole picture. Einstein came along and he asked, how does gravity work? And what he came up with was, it was less of a force and more of a result of something. He described gravity using space-time, a sort of infinite fabric all over space that is curved by energy, momentum, and mass. The more mass or energy present in a place, the more space-time curves. So when you have all of this stuff, all of this hydrogen and helium together, even though it's really light, you get enough of it in one place, it starts to make a curve. A bigger curve, well, what happens when that curve gets bigger and bigger? Well, stars.
So, for the fourth dimension is
Time.
time.
Yeah.
Yeah.
Can't see it because if you ever look at any diagrams of space-time, you'll see it as it comes through like this. It's infinitely stacked on top of each other as time goes through. You can go up, but you can't go back. All right. So right. So you got enough, like I said, you have enough hydrogen and helium and enough dust all packed together, and well, what happens? A star is born. It starts collecting, and it gets hot, really hot, and a protostar happens eventually. And the fusion that causes that is usually hydrogen, because well, there's most of it there, and that constitutes the core. Alright, and as it grows in mass, it starts pulling more and more stuff in, and it grows, and it gets bigger and bigger and bigger, and eventually becomes either a main sequence star with low mass or high mass. So our sun, outside, you can't really see it from here, is low mass, kind of. It takes a while, but eventually it does run out of hydrogen to burn. And after hydrogen, it starts burning helium, then carbon, then neon, then oxygen, then silicon. But it stops at iron, because at iron it starts to take energy to trigger the fusion reaction rather than getting energy out of the fusion reaction. So eventually gravity starts winning over the fusion, pushing outward. And what happens then? Anyone know? No? Gravity starts?
Supernova?
Possibly. In the high mass stars, yes. Low mass, eventually it just starts going out, yeah.
So the curve then turns into something burning?
You have the curve, all of this gas, the hydrogen, helium, more of it starts collecting, and it starts rubbing together, the pressure increases, and that starts triggering small fusion reactions. Keep in mind, this is taking place over very long periods of time.
Like millions of years?
Try billions. Well, millions, sometimes billions, usually hundreds of millions for stars. Yes.
So just maybe to clarify a link there, he's, I believe, talking about the curvature of space-time as it relates to the gathering of mass. So the deeper the curve that you have, the more mass is able to gather, the more star stuff, essentially. So that's what, like,
And then within
forms
this
of stars.
curved
Yeah.
space,
Yeah, pardon?
within this curved space, it's accumulating a bunch of mass.
Yeah.
Things are rubbing against each other and creating
Yeah.
burning.
Think about like
A
remember-
literal fabric.
Yeah.
Think about a literal fabric.
Yeah.
You have mass, say you have a ball
Yeah.
in the middle of this fabric. It's gonna make a dent into it.
Oh.
And let's say you have a ping pong ball then swirling around.
Mhm.
It's gonna get drawn towards the bigger mass. And when that happens, the dent gets bigger. And all these little small amounts of mass add up and grow bigger and bigger and bigger. And eventually, a star can be born, or other things, but we'll get to that later. All right. Right, where was it? Right, the dying part. So it runs out of hydrogen to burn, it gets to iron, the iron core happens, and it can go supernova and send it out across the universe. This is the leading theory, and a pretty accurate one, for how elements can get distributed throughout the universe. Because during these cycles, other elements get produced on the side, like sodium and whatnot. But this all takes a very long time. It's very time intensive. So how else can this happen? Well, let's get into it.
I like that.
Yep, good. So enough mass packed densely enough together, and I'm talking very, very densely, can collapse in on itself and create something with gravity so strong that nothing can escape, not even light. I'm sure you've all heard this before. Anyone know what it is? Because I do, I know you know.
Is that a black hole?
Correct.
All right.
Black hole. The measure for this size needed is called a Schwarzschild radius. This is it right here. Imagine this over here is, say, a star. It starts collapsing in on itself. If it reaches this radius right here, it will collapse in on itself and become a black hole. Everything has one of these, including you. For our sun, it's about 3 kilometers. The Earth is about 9 millimeters. Human is, well, let's see, 10 to the power of negative 23 centimeters, smaller than an atomic nucleus. It needs to get very, very dense. So you're gonna need things of very, very large masses. Our sun, it wouldn't be possible. It's too small for it to become a black hole. So what type of black holes can happen with only this limited amount of stars? Well, there are different types of black holes. There's our confirmed types. We have stellar mass and supermassive. Get into those bits. Stellar masses are 3 to 100 solar masses. Supermassive, get to that in the next slide. Don't worry, get there. Intermediate mass black holes are unconfirmed because they're nearly impossible to detect. Practically confirmed though, we just haven't had any visual examples of them. Theoretical, these are fun ones. We have something called a Kugelblitz, which is German for ball lightning. Why does that matter? Well, remember how I said momentum and energy can also curve space-time? If you have enough light, photons gathering in a single place, you can make a black hole from light. Weird thought. Technically possible, but you would need enough light from the sun over the course of a few billion years.
a huge amount of photons densely packed into a very small.
And not small enough space. Basically, all the light that the sun would emit over, say, a few billion years in one single place.
And is the theory that this can pierce
The math, yeah, under the math, it can happen because momentum, light carries momentum, and momentum curves space-time. So if enough, it's a big if. That's why this is only theoretical. Technically, realistically, not actually possible. Primordial black holes are pretty simple. Remember when I mentioned very early moments of the universe, it was a very hot primordial soup, all that stuff there? It's theorized that little tiny black holes, big and small, popped in and out of existence very quickly, or maybe just remained in those first moments of the universe. This right here is, well, this was the first ever image of a black hole of the galaxy Messier 81. It's not much, doesn't look like much, but I think it's cool. Yeah.
What kind of black hole is the one in Interstellar?
Interstellar, that would be a supermassive black hole. And actually, that black hole bugs me a little bit because so much of it is accurate except a single part of it, and keep that in mind, I will tell you exactly what was wrong
Dropping
with
into
it.
and surviving?
Dropping into and surviving? Probably not. That's a whole thing. If you have any questions about what happened if you fell into one, I'll get into that at the end. So any questions? All right. So we're focusing on supermassive black holes today. They contribute to most of my idea, but what are they? Well, it's a type of black hole that is greater than 100,000 solar masses. Our sun is just one of those, about 1.989 times 10 to the 30 kilograms. Unfathomably big. So imagine 100,000 of our suns just in one place. That's a supermassive black hole. Nearly all galaxies have these at their centers. Sagittarius, yeah?
And you said that that one place is 3 kilometers?
No, that was the Schwarzschild radius for our sun. If our sun were to collapse into a black hole,
Yeah.
all of it, with its current mass,
Right.
would need to be condensed down while maintaining that mass to 3 kilometers in radius.
What about for a supermassive black hole?
Supermassive black hole? It depends on what the mass of its star was.
Yeah.
If you want to know how they form?
But like, I'm just curious about what would that radius be? Would it be like the size of a football field?
A little bit bigger than that.
Yeah.
Supermassive black holes, nothing's confirmed about how they form yet. I do have an extra slide for that I could get into at the end.
Sure.
No worries, yeah, I'll get back to that later. More
Sorry.
No. Also, well, where was it? Okay, so all galaxies have these at their centers. Sagittarius A star at the center of our galaxy is a supermassive black hole. Andromeda, the one I showed you before, Messier 81, where was that? This is a supermassive black hole too. Almost all the ones a lot of the ones we know of are supermassive because they're easy to detect. They are really powerful, really big. Think of the Milky Way, for example. To get from just where we are, which is almost on the edge, to the outside, it's 100,000 light years. It's a ridiculously long distance. And a black hole is keeping all of this stuff, all of these stars, solar systems, straight planets, exoplanets, it's keeping all of those under wrangle. It's keeping all those together. Just this one thing right at the middle. All right. Okay. What do they look like though? Okay, so I showed you what they look like, but that's kind of a blurry image. Well, right here is a little diagram. Okay? It's a little much. Don't worry, I'll get into it. So, right here, this little shadow part is called the event horizon. It looks like, think of it as the surface of the black hole, even though black holes do not have a surface. It is not a physical boundary. What happens here is the gravity gets so strong that nothing, not even light, can escape. So when not even light can escape, it becomes a void, just darkness. Whatever is past that, you cannot see at all, period. And speaking of things you can't see, right at the center is a theorized point called a singularity. Singularity is not an actual point, but it is the center where space-time curvature, remember how I said that space-time curvature, the more mass present, it gets more of a dent? At the center of a black hole, it's theorized that it would be infinite density. So technically, it would become just, imagine a fabric just pressed down infinitely deep. It is a paradox. It is not real, but it is the current idea for what is at the center of a black hole. We cannot know because, remember, light cannot escape, and thus information cannot escape. This little ring right here is called the photon sphere. Right here, it's about 1.5 Schwarzschild radii away. Remember, that's just from the center to the event horizon is one Schwarzschild radius. That's just one of them. So 1.5 away is the photon sphere. Here, light, it remains in this sort of unstable orbit. It can either go in from there, out, or stay in for a little bit longer, and it creates this little effect where it creates a ring right around it. All this stuff here, this is called the accretion disk. It's an accumulation of stuff that it's catching from space. It could be asteroids, rocks, stars that it's absorbing, anything. And if you notice here, it's brighter on one side than it is on the other. That brings to my point of what I didn't like about the interstellar black hole. This is called Doppler beaming, something called the Doppler effect, which, you know, ambulance, they drive by, it gets loud, 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 then quiet. What the Doppler effect is? Waves. When it's traveling towards you, it gets shorter. They're hitting you faster, it travels away from you, it gets longer. So when the black hole is rotating like this and light's coming towards you, it gets brighter. Away from you, it gets darker. That's what that is. These are rotating so incredibly fast that it is actually stretching out kind of the light. It's stretching out the light. Not just the gravity, but the sheer speed that it is rotating with. It's not shown here, but in certain supermassive black holes, coming out at the bottom and top would be relativistic jets. In the accretion disk, it is incredibly hot and really tightly packed together. So fusion reactions can happen there. And nothing is confirmed yet, but it's going to reach my original idea. But sometimes matter from the accretion disk comes up to the poles and shoots out with incredible power for light years, sometimes hundreds of thousands of them. So just understanding kind of some basic anatomy, it's going to bring us to the final piece of information, kind of what I call the black holes of life and death.
Bless you.
This right here is the unified AGN model. What is an AGN? That's this. It's called an active galactic nuclei. What they are? Well, at the center of some galaxies, this is where the supermassive black holes are actively accreting or gathering very large amounts of matter, insane amounts of matter. It sometimes produces so much energy that it can outshine the rest of its galaxy entirely. Just a quick question, raise your hand. Who thinks a star is the brightest thing in the universe? Who thinks a supernova is the brightest thing in the universe? What about a galaxy? Wrong. It's these guys. So, aforementioned particle jets right here, these relativistic jets, when it is pointed directly towards you, it can be the brightest thing in the universe. There is so much matter accreting here, and it's getting so incredibly hot that it becomes bright enough to the point that we can see one of these that existed, I think, less than 1 billion years after the start of the universe. We know of one of these that is about 11 billion years old, 11 billion light years away. That's how bright these are.
And just to be clear, brightness means an accumulation of mass, an accumulation of photons.
No, just say there is so much matter and so much stuff accreting in the accretion disk here, and it's so tightly packed together. Because an active galactic nuclei is different than other supermassive black holes. Regular supermassive black holes, like the one at the center of our galaxy, they're there, they are taking in matter, but it is, for our sakes, a relatively normal amount. It's nothing crazy. With these, they existed much earlier in the universe. They can still exist, but they, for the most part, existed much earlier in the universe when there was much more matter and stuff to accrete together. When that happens, it becomes incredibly hot. Heat creates brightness, a lot of brightness, incredibly, incredibly bright, to the point that it can outshine the rest of its galaxy. So imagine, see this region right here? You have the black hole, ignore the torus here, or right here, this section here. Imagine that is the size of our solar system, from all the way, say, to Neptune, all the way across. Imagine a region that big being brighter than the Milky Way itself, all of the Milky Way. That is what an active galactic nuclei is. It is supermassive black hole at the center of some galaxies, usually existing much earlier in the universe, that accretes so much matter and so much stuff that it gets hot enough and bright enough to the point that it outshines its galaxy. It can, not always, usually, yeah. All right. Like I said, it's likely that they won't be forming, but as I'm sure you've heard, the Andromeda Galaxy and the Milky Way Galaxy are going to collide in the distant future. When that happens, it is likely that the supermassive black hole at the center of the new galaxy, Andromeda, will be an active galactic nucleus for a period of time. Okay, why is this important though? This seems kind of random. Well, it brings me to my conclusion, right? While black holes may not have been required for the ongoing sustaining of life on our planet, what I'm proposing is the idea that supermassive black holes, specifically the AGNs, the active galactic nuclei that I mentioned earlier, may have aided in setting the stage for life by acting like a sort of factory, converting simple hydrogen and helium into the more complex elements necessary for life, like carbon, nitrogen, oxygen, phosphorus, sulfur, in their accretion disks. I'm thinking that from those reactions, then the relativistic jets of them distributed them throughout the universe like a sort of interstellar highway, giving these biogenic elements, say, to a planet like ours. All right.
Good question there. If we're assuming